just kind
Okay. Right. Welcome everybody to our monthly geology meeting. And today we are privileged to have Martin Bates with us from Standard Geophysics in Canada, who's going to be talking to us about aerial surveying. And Martin has just sort of told us he's been to every continent on the world, on the globe. So I'm sure you've got lots of interesting things to be telling us about, Martin. I'll hand over to you.
Okay, great. So I have a PowerPoint presentation to give. So I'm gonna see if I can make this work. Okay, okay, I've got to find a way to share my screen first because I can't see the screen to share it anymore.
Oh, it should be down
That's
at the bottom somewhere.
yes. Where are we? More, I think. Here we go. Share. Uh, okay. It's saying one person can. Oh, here we go. Hopefully you can see the presentation. If I start this presentation from the beginning. Okay, how does that look? Got a nice
That's
picture of an
wonderful.
airplane with my name underneath it. Okay, so just a little bit of intro about myself. I've been working at Standard Geophysics and Airborne Geophysics for 30 years now, plus. Did a geology degree at the University of Durham and a PhD in paleomagnetics at University of Leeds, and then a couple of postdocs here and there in Canada, and then in Zimbabwe, and then ended up in airborne geophysics, and I've been here ever since. Worked all over the world, literally doing surveys. So I just want to give a little bit of a run through about what it is that airborne we do in airborne geophysics, and I'm going to concentrate on the methods I know the best, which are the ones that Sander does. We don't do everything. We do quite a lot of the methods. And what you can see here is a typical survey airplane that we fly, a Cessna Grand Caravan taking off in Africa on a project. And you can see a little tail out the back if you look carefully. That's where our mag sensor is, and we're going to get onto all of that. So we're going to look at aeromagnetic surveying, which is kind of like the most standard methodology that's been around for a long time. We were talking about what's changed and what hasn't changed in these techniques before with the presentation. Aeromagnetics really hasn't changed a whole lot over the years. It's pretty similar to what we did all that time ago. Air gravity, that's something that's actually developed. It wasn't even a thing when I started working, and Standard Geophysics is now a world leader in that area. And our air gravity meter is the most accurate gravity meter that you can fly in the world, and that's proven. And that before that there wasn't even a possibility when we first started. Gamma ray, natural gamma ray radiation surveying, uh, some frequency domain electromagnetics. We'll touch onto that. We're not going to cover time domain electromagnetic. I'll refer to it a little bit as we go along. That is actually the more common of the two electromagnetic techniques. And there's also gravity gradiometry. I should mention that. It's really not fundamentally different from air gravity, but the measurements are of the gravity gradient, not of the gravity directly. But we don't do that at Sander. We used to, but we don't now. So we're going to start off with magnetic mapping. And what we're talking about here is we're really magnetic mapping magnetic susceptibility. This is a property of minerals and in bulk of rocks. And primarily, we're talking about magnetite as being the most common mineral that generates a magnetic field. It's generated in response to the Earth's magnetic field. The Earth's magnetic field is what actually creates a secondary magnetic field in the rock itself and produces an additional magnetic field which is related to the rock. And that's what we're interested in. We can subtract away the Earth's magnetic field because we know what that is, and we can reveal the measurement, the differences in the magnetic field as a result of the rock property. It's a very standard method. It works basically down to the Curie temperature in the Earth, which is down around 30 kilometers down. It gets too hot and things aren't magnetic anymore. Um, Greater detail from shallow, less detail at depth, but still you get a lot of structural information as well as direct information on ore deposits if they happen to have a magnetic response. And it doesn't have to be high or low, it just has to be different. So it's always about we talk a lot of the time about properties, but a lot of it is about contrasts in properties. As geologists, you know that there are rocks of different kinds. They're all next to each other. If they all have the same magnetic property or whatever property we're targeting, we're looking for, if that, then you won't can't tell them apart. But if they are contrasting with what's next to them, then you will. And so certain things will be obvious in certain geological certain circumstances and other times not. We're looking the magnetic minerals in the, if it's in a target directly, as I mentioned, magnetite, pyrrhotite, ilmenite as well, hematite to a lesser extent also plays into this. They all have a magnetic response that we can measure. Often alteration causes reduction in magnetic field locally, and that can be related to mineral deposits, which where alteration can result in mineral bodies. And so that's where the negative effect can come in. And then we can also just map variations in rock types depending on just the bulk lithology, and you see structures breaks in the magnetic field. You see folds and contacts between different kinds of bodies. This is what a magnetometer looks like. So the actual magnetometer is the thing on the right there. It's about the size of a can of beans. The magnetic field has to be aligned either to the axis of that thing or to the long axis or to the circumference for it to pick up the field. It's a cesium pumped vapor magnetometer, and it's measuring magnetic intensity. It is possible to measure the vector of magnetism in the air, but it is difficult and more just generally more challenging. So for the majority of magnetic surveys, we're just measuring how strong the magnetic field is, what its overall intensity is. And this magnetometer emits a pulse of frequency, which is directly related to the magnetic intensity. So when we put this onto an airplane to fly it, and you can do this on the ground, you can do it anywhere you like, you can put it in a drone, but airborne is all about flying large areas relatively cheaply. You get more detail the lower, closer to the ground you are. So if you do a ground survey, then great. But then you have to slog it with this thing on your back. And sometimes access is very difficult, maybe even impossible, and areas can be quite large. So we're talking about an exploration technique which is somewhat at the front end of exploration, covering relatively large areas at a good detail, but not the highest possible detail. And you can then follow up in areas of interest. But certainly for mapping large areas, you're not going to want to do that on the ground. So you can see the bottom right there, pretty standard operation there. We've got this thing called a stinger at the back of the airplane, and the magnetometer is sat right out where that little red tip is. And the reason for that is you want to get it as far away from everything else that's magnetic in the airplane. There's lots of things going on at the front end with the engine and the avionics, which would create local magnetic fields, and you want to be as far away from there as you can. So we stick it right out the back like that in the stinger. Um, we have to. That's basically the quietest spot we can go with. With the helicopters, you can see if we want to fly lower, then usually our surveys we're operating at around 80 to 100 meters above ground in a fixed wing airplane. We don't really fly a lot lower in a helicopter, but when you're flying in rugged terrain, it's harder to stay close to the ground. You can imagine if you've got a hill coming, you can't really kind of like scud along at 60 meters above the ground if there's a mountain coming up, because you're just going to fly into it. So you have to start to climb and up and over, and that reduces the resolution of your data in rugged areas. So if you really want to get good data in rugged areas, a helicopter is your better bet. So we've got two options for the helicopter. Top right is we have a stinger there, but we can't put it on the tail because there's stuff going up on back at the tail with the rotor there, which isn't going to allow that. So we reverse the thing and stick it out the front and instead. So that's okay. Better still, if you can do it, is you can have what we call a bird. That's that bottom left-hand one where we put the magnetometer in a suspended structure that actually it's aerodynamic. So when we fly, it stabilizes and drags about 30 meters below the helicopter. And there it is operating in Greenland in that situation. That's really great data. You get very, very quiet data down in that bird because it's so far away from any magnetic interference in the helicopter. So why wouldn't we always do that rather than put it in a stinger? Well, the reason for that is that sometimes you're not allowed to have a bird if you're flying over any kinds of areas where it's populated. It's considered a hazard, or over, and also in particularly rugged terrain, it's very easy to smack that thing into the ground because you're physically separated from the helicopter. So there are practical considerations and legal considerations that sometimes mean that the stinger is the way to go. The one on the top left there, that shows a full array of four magnetic sensors. Now we're measuring not just the magnetic intensity at one spot, but how it's changing. And that's far enough apart that we can tell the difference, from side to side and up and down and front to back and get magnetic gradients in multiple directions. And that can give us a better way of filling in the gaps. Because what we're going to do here is we're going to fly up and down survey lines, parallel lines, at a certain spacing. And the closer that spacing is, the more detail you get, but of course, the more costly that becomes. So if you can space the lines out a bit wider, it's going to be cheaper, but then you have to interpolate the data in between the lines. If you know how the magnetic data is changing perpendicular to the lines by leveraging gradient like this, then you can do a better job of filling in the gaps between the lines. You can always do it without that, but it's just an improved resolution methodology. So just a little diagram to show what we're actually measuring. We're measuring a total intensity, which is that delta B. Delta Z is vertical, delta H is horizontal. It's a vector, as I mentioned, but we're only measuring the total field, and that's just a magnetic response from a simple unipole, which is really a non-existent thing. It's just a theoretical thing. Every pole has an opposite pole, as we know in magnetism. So, but if you're measuring just the effect of one of them, what you see is with the overall field, you have a magnetic vector, and this vector is going to be dependent on where you are on the Earth. It's going to be like almost vertical in the North Pole. It's horizontal near the equators, and it's vertical, but in the opposite direction at the South Pole, and everything in between. And how that responds and creates a secondary response in the pole is what you're seeing in the magnetic anomaly. That's the extra magnetism that's being created. And because magnetic flux links around, you can imagine a bar magnet and how it's sort of that typical kind of shape of magnetism. There's places where the induced magnetic field, due to the extra magnetism, is in the same direction as the field that's inducing it. And there's places where it's opposite. And so that sometimes the same body will cause both negative and positive effects in the field that we're measuring. And this is in addition to whatever the total field is. So the total field will be something huge, like something typically in the like maybe at the mid latitudes, 60, 70,000 nanoteslas, that sort of range. We're talking about add plus or minus on top of that of usually anomalies of like tens of nanoteslas to hundreds of nanoteslas for big ones, superimposed on that Earth's magnetic field. We subtract away the Earth's magnetic field, we recover the anomalous magnetic field, and that's what shows us what's going on in the subsurface. This kind of gives you a sense of rocks and minerals and how they affect what kind of susceptibility ranges we're talking about. Mentioned that magnetite is the most common, and this is the most common of the magnetic minerals that occurs in nature, has the biggest overall effect. And you can see it has very high susceptibility. But of course, it's only a small part, usually a small portion of the rock. So if you look at some of those, something like a banded iron formation has a lot of magnetite in it, and that is still very, very highly susceptible. Yeah, but basalts and dolerites are pretty strong. And then you get down to sediments that are awfully very much not magnetic, and things like limestones and the like really have like no response at all. So there's a good range of responses here, but you can see how it's non-unique. I mean, you can see that if you look at those rock types, if I go to gabbro, is it different from a granite? Well, really, no. It's pretty much the same thing. Um, so you're not going to be able to tell just from the magnetic susceptibility and the strength of the anomaly what rock type necessarily you have, but you are going to be able to eliminate what certain rock types you might be looking at. So a lot of geophysics is about knowing what you don't have as much as about what you do, and then cutting down on the possibilities. And none of this is done in isolation. We measure things, but when, of course, these things are studied and used in reality, they're combined with all sorts of other geological information and knowledge of what is likely in any given geological terrain, from from studies over all the geological studies that have gone on over all the years. So you know what it's likely to be in given circumstance, and you can eliminate things in that way too. So you're going to leverage all the information. This is going to be in addition to that, and that's going to cut down on what it is you're looking at. Now, here's my favorite technique, as Ian will know because he was with me on the project that we did up in the north of Scotland. I love gamma ray spectrometry. And this is partly, I guess, because I did start my life in geology as an undergraduate in the University of Durham, and it's a surface mapping technique. Basically, you're mapping gamma rays that emit from only from the top 20 centimeters of the surface of the ground. And if you know about the ground, is obviously the rocks don't always stick out through the ground, so sometimes you're measuring the soils. In fact, most of the time you're measuring the soils and overburden. So you have to take that into account when you start to interpret data. But actually, even though soils move and regolith moves and rivers take soil, sand from one else place and deposit in another, and glaciers do the same. Even with all of that going on, and you take that all into account, you can still see a lot of correlation between underlying surface rock, hard rock geology and the overlying uh, overburden. And of course, there are times when the rocks stick out too, and they will give you nice strong signal because they're nicely uneroded and often have good gamma ray signatures, and then you can get a direct measurement on those. We're really talking about three elements. We'll look at the spectra in just a minute, but potassium, uranium, and thorium are the elements which they're relatively common in nature, particularly potassium, and also it generates somewhere in their decay series, and it's not a single decay, but it is for potassium more or less. But for uranium and thorium, it's a whole cascade of decays that go from the parent to the final stable daughter. Somewhere along that line, there's a gamma ray that is emitted that is strong enough that it will go far enough in the air that we can detect it. It has to be that something which we can pick up in the air, and we can get this up to maybe it depends on the strength, but we're talking usually around up to 300 meters up into the air. You can still detect, and even beyond that, if it's strong enough. 450 is about the maximum we generally go. Sometimes it's less if it's weak. So again, we're looking at mapping, exactly lithology, changes of lithology, which you can actually see boundaries between rock types and the like, but also alteration related changes within a particular lithology that can again lead you to potential mineral bodies. And sometimes directly, in this case, you actually might pick up something of actually that is you're actually looking for, which is uranium. One of those rare occasions where you might actually detect directly the thing you're looking for with the method. A lot of the time with the geophysics, it's indirect. You're looking at circumstances around the if you're looking for a particular ore body or structure, um, it's not that you don't necessarily know it, see it right off. You have to take all the various information into account. But with its uranium, you can actually potentially see it glowing away right on the surface with a nice strong uranium signal. A little bit of water over the top, and you don't see anything. Basically, a meter of water, and it's gone because it just absorbs all the radiation. So you don't see anything from lakes or rivers, and of course from the sea. Actually, the sea actually has have a little bit of its own gamma ray signature. It's potassic, a little bit. We know the sea is salty, but it's got potassium as well as sodium, and you can actually measure that. You can see that in the signal. It's weak, but it's there. Not that it's particularly interesting, but it's just like, yeah, there it is. So what does a spectrometer look like in our world? That box on the left actually has five of those things on the right. inside, four in a row and one on top. That's why it's got a kind of a tented shape to it. That thing weighs a ton. That's a four guy lifting job to pick that thing up and put that into the airplane like that. I've lifted one with three other guys, so I know it's you do not want to drop that thing on your toe. The thing in the black box is actually a thermal wrapping around a sodium iodide crystal. This thing is doped with thallium and it scintillates. It emits a photon of light for gamma, which is of an intensity related directly to a gamma ray, an incident gamma ray energy. So you have a relationship between the gamma ray energy and a photon of light. It's picked up by that photo multiplying tube at PMT on the metal thing on the near end, gets amplified, goes through the photoelectric effect, creates an electron, which is also of energy related to the energy of the incident gamma ray. And then that gets amplified through the PMT to a pulse of electrical pulse, which we can measure. And so we're measuring basically just measuring this radiation. If you can imagine, you got the classic kind of Geiger counter idea. You're walking along and it's like crackling away. Radiation isn't consistent. It doesn't like happen all the time as a perfect flow of just click, 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 click at a certain rate. It's a stochastic process where you get semi-random radiation, but over time, it's if you've got more of it going on, you get more radiation. So we measure over a period of a second, and we aggregate all the data within a second. And that time we cover about 70 meters, so that kind of sets down a resolution limit. The longer you can measure for, the more you get a better average of the count rate and you get a better signal and a better knowledge of what the count rate is. But if you measure for too long, then you're not going to get resolution on the ground. So you have to balance those two things off, and a second is about right for that. This is a spectrum of radiation that you might expect to see if you're measuring it in the ground, and you can see the three elements which we're measuring. It's actually thallium 2.61 is a decay in the thorium series. So you start with thorium, it goes to a bunch of other elements on down to eventually another. I can't remember the stable one. I think it's layered of some sort. Anyway, thallium's on the way, and that gives you an energy which you can detect. It's a high, strong energy at the top end of the energy scale. There's a bismuth 1.77, which we can pick up, which is related to uranium decay series. And then there's a potassium 40 right there, which is actually measuring the element, the decay of the element you're interested in, the actual source element itself. It's slightly complicated, but it's basically a single decay. The reason that it kind of has this wavy look is that the gamma ray detector doesn't always get it quite right. There's a few red ones in there. Those are man-made ones which can come and sometimes get in the way. Sometimes that's what you're after. Sometimes you actually want to like measuring cesium-137. That may be actually what you really want to measure, and then that would be superimposed on top of that. But if you're free of any strong effects from man-made elements, that spectrum is what you're going to get, something like that. And what actually happens is that any energy, when it passes through the atmosphere, it interacts with matter and it scatters into lesser energies. So that's why you see all those high energies at the left-hand side. That's all lots of low energy, but all that is scattered energy from the higher ones. So they've just become lesser amounts of energy, but their sources is the original higher energies, but you can't really tell what that is. It could come from any of the elements which are higher up in the sequence. But you can see the peaks related to the natural ones: potassium, uranium, and thorium, potassium, bismuth, and thallium, actual elements. That's what we're going to be able to pick up. And what we actually do is we measure in a range of energies either side of these peaks. Those are the parent elements: thorium-232, uranium-238, and potassium-40. And the reason for that is that the spectrometer doesn't always get it right. It thinks it's an energy, it might get the energy a little bit higher or a little bit low. when it calculates what energy it's getting. So that's why sometimes the energy is that's why you get that sort of peak instead of a straight a line exactly on the energy related to that gamma ray, because the spectrometer isn't precise enough to always calculate it in the right at the right energy. But you can see clearly that it's related to that high point in the middle, and all of the gamma rays in there is related to that, or from an energy higher up, which is scattered down into it. So thorium will scatter down into those uranium and potassium. Uranium will scatter into the potassium, and so you have to account for that. And we have methodologies to do all of that to calculate what how much of that energy will turn up in the other areas of interest there in those other elements. You see a little cosmic arrow there, that everything above three MeV or 3000 keV electron volts is cosmic radiation. This is radiation that actually emanates from above, from the sky. It's not directly measuring the radiation that's coming from the sun, but it's measuring a secondary effect of energies from interactions with the upper atmosphere. And we have to measure that, and we have to account for that because that gets scattered down into all of these other energies as well. You see a total range there. We're measuring sort of all of the peaks that are related to those decays, because there are multiple peaks. As I mentioned, in thorium and uranium, there's multiple decays. So you've not just got the one or two, they've got other little peaks related to other decays in the decay series. We want to capture all that in that total natural radio element area, but avoid just all of the scattered stuff, which is not original energies from the gamma rays. And I will mention the one I mentioned earlier, the box had one on top, and that's there to monitor for radon gas. Radon is annoying. It's the most annoying thing about gamma ray processing because it's part of the uranium decay series. It happens before the bismuth that we're interested in, which means that you can't tell when you measure whether you're measuring radiation from the ground, which is due to the rocks and soil beneath you, or from radon, which happens to have floated in from somewhere else. Most of the elements in these decay series don't move; they're immobile. But radon is a gas, and it does move. And so you might be picking something up which is not related to your local geology at all. It's come floating around from somewhere else. The upward detector is sat above the other detectors in order to be shielded. Basically, the ones beneath it more or less shield it from the radiation from below. They absorb all the radiation coming from the ground. And so it only sees radiation from above, which would be cosmic, and all radon that's around you. And we have methodologies to calibrate for that. There are other techniques, but that's the most standard one to monitor for the presence of radon gas and subtract it from the radiation measurements that we're taking to get what we want, which is the radiations related to the surface of the Earth. Here's some ranges of count rates or concentrations. We calibrate we measure counts, just a count rate 1, 2, 3. How many counts of this gamma ray did we get? But then we can calibrate that using an instrument where we measure it against a known concentration of that element, and we can come up with a concentration value, which is just a simple ratio to the number of counts depending on the system. And you can see here, these are kind of typical ranges of concentrations for potassium, uranium, thorium. Thorium is usually 4 times, in parts per million, 4 times higher than the other two. But you see potassium is expressed as a percentage because actually it's way more concentrated than uranium or thorium. Uranium and thorium measures in parts per million. So they're really quite small amounts, but we can still pick them up. And as with the magnetic susceptibility, you see a range of values for different rock types on the left there. You can see something, but you can see, for example, ultra basics are really, really low in potassium, and you will see that if you fly over a dunite or something like that, or an ophiolite complex, the potassium just down it goes, nothing there. And there isn't much else that's really like that. So that's almost diagnostic, but you can see carbonates also very, very low. So how can you tell the two apart? Well, There's geology, of course. There's magnetism. That's going to be different. Those ultra basics are going to not be are not going to be non-magnetic, but the limestones probably are. So, you can see that, you have combinations of things and you start to be able to tell what you're looking at. It's not all just one thing is going to tell all. It's multiple methodologies help you. Plus, just as I said, geological knowledge, geological mapping, all those sorts of things all come into play when you're interpreting this kind of data. So gravity, as I said, wasn't this is actually to me still extraordinary that this is possible. Yet we measure it, we repeat, we get the same thing. It's like, yeah, it really does work. And and you have to consider what we're looking at. What we're doing is we're measuring changes in density in the rocks. Um, Now, obviously, the majority of what you measure is the Earth, the pull of the Earth. It's just, it's got a strong gravitational pull, and you've got a very, very small change in that, depending on how dense the rocks are that are closest to you or in the subsurface. And more bigger bodies at depth will still create bigger responses, and smaller bodies near the surface will can create a similar response, but over a smaller area. So you're looking down into the earth, and in theory, it goes on infinitely, but of course, the signal does drop off exponentially. So you're not going to see it forever. You're not going to see responses all the time, but you can get good mapping of down to like mapping of a basement basin interface. Like a sedimentary basin. If you want to know the structures at depth, which oil companies frequently do because they're looking for traps related to structures at the base of the sedimentary sequence. This is perfect for that. But the thing is, well, as I say, you're in an airplane, and we all know about pulling G's. You're bound, and you've been in an airplane with turbulence probably, and you've had that moment when your stomach gets left behind when you're flying over the Atlantic. Well, okay, now you're at 100 meters or less above the ground, and I can tell you it's a whole lot bumpier down there. It's you've got a lot of ground effect of winds blowing over hills and things causing you to jump up and down, and thermals and the like, and you're bumping up and down all the time. And that motion of the airplane up and down is way, way, way stronger than the effect that we're looking for. It's just like many orders of magnitude bigger. So how do you deal with that? You have to be able to tell the difference between the two. And the reason that what we do is first off, we have very, very sensitive instrument. It's let me see if I'll show it actually. We'll talk about what we can do with it first, and I'll show you the instrument in a minute. Yeah, so here we're looking at, as I say, dense, obviously changes in density. You can see bulk changes or across faults or fold structures, discontinuities in the subsurface, looking for particularly dense or less dense lithologies, and also often elements in deposits quite frequently are quite dense. So you can sometimes detect a a mineral deposit directly with gravity. More so for mineral deposits, more like gravity gradiometry is actually a bit better for that. But we can pick up the bigger bodies, maybe 700, 800-meter wide bodies with the gravity meter too. So we just go on to the instrument. There it is. That's the one we built. It's got like military grade accelerometers inside that thing for measuring vertical and horizontal gravity pull. It keeps itself flat relative to the ellipsoid of the Earth, which is a mathematical equivalent of what the surface of the Earth is, because it detects the rotation of the Earth and orients itself using gyros and orients itself perpendicular to that. Um, that isn't perpendicular to the vertical gravity because that's often a equipotential surface, which is the geoid. So when we're measuring the vertical and horizontal components. That's how we can see what the geoid is because of it. We can see how deflected from the ellipsoid the geoid vertical is relative to the to the to the mathematical version of the Earth, the circular, the nice oblate spheroid that we would like to be if we could. Um, so we have to measure that we obviously have to have these very sensitive accelerometers, but we're also accelerating up and down and left and right to some extent as we're flying. So we measure very accurately with GPS. And we talk about the difference that GPS made, not just to locate ourselves, because obviously every time we take a measurement, we need to know where that measurement was, and we use GPS for that. But we also use it to correct our gravity data, and we use special algorithms that are they're designed to more optimize not just your absolute position, but how your position changed, where you were a tenth of a second ago. Because we're actually measuring at a higher rate of like 160 hertz, but we end up correcting at 10 hertz. And then we downsample it to 2 for our final data after some filtering. But the corrections are done at 10 hertz. So basically, every tenth of a second, we need to know where we were relative to where we were a tenth of a second ago before. That's the accelerations that we're interested in. That's going to tell us what G's we pulled in vertical and horizontal as we were moving at that time, and then we can correct for that. And and when we do our GPS, we do lots of GPS. We measure it in all sorts of different combinations of the signal that is available to you. We have lots of redundancy. We have multiple antennas to account for to average out effects and get the best possible calculation of that change. And with all of that extra processing of GPS, we're able to recover the vertical and horizontal gravity components. So yeah, bit of a miracle really, but it works. Here's our density range. And actually here, if you look at the numbers at the bottom, the density range isn't that big. 2.67 is sort of average Earth's crustal density. There's some very low density things, usually sediments of one sort or another. There's salt down there and limestone. Sandstones aren't, in the twos or less. Unconsolidated material, as you can see, soil and alluvium is particularly low. It's not packed together. And then you've got some really high density things. So you can see like chromite. Well, there's something you might want to find. That looks like an interesting thing. Yeah, that's dense. So, fortunately, if you've got enough big enough body, a chromite pod, you might even see it directly in the measurements. But you'd have to have really close, accurate measurements because chromite pods tend to not to be very big, so they can easily be lost in the geological and geophysical noise. But you can definitely see differences in granites and gabbros and things like that, and you see structures and changes in the subsurface, both shallow and deep. So another string to the bow when it comes to differentiating between rock types and seeing contrasts and boundaries in the subsurface. Last method I want to mention, we're talking about conductivity. In this case, the other methods are all passive. You're not doing anything to generate the signal. It's already there. The magnetic field is in the earth. It's there. You get your compass out. It tells you where north is because the magnetic field exists. The gravity's there, otherwise we'd all be floating off into space. The gamma ray energies are there, whether we like it or not. If you live on a granite, you're going to get more radiation than if you live on a limestone. You know, you can risk that. I take that as a fact. For EM, electromagnetics, you have to create the response. There are currents flowing through the Earth, but they're not strong enough for us to detect So what we need to do is create a response in the ground. So we're looking for conductivity. Um, you want we talk about actually we talk about conductivity and resistivity. They're just the reciprocal of each other. Gets a bit confusing sometimes because we actually often measure resistivity. We talk about resistivity. It's just the opposite of contact. It's just 1/conductivity. We have a limitation of how deep we can measure this. Really, basically for our frequency domain system, which I'll talk about a little bit more, we're really talking about the top 120 meters of the ground at best. Some of the time domain systems aren't so good at shallow detection, as we'll talk about, but they're good, much better at getting down to depth. They have stronger power. But we're talking at the best, the most powerful systems claim to get down to 900 meters, but really we're talking like 500, 400, maybe even less. It depends. If you have interesting enough, if it's actually less conductive, the ground, you get better depth penetration. If the ground is very conductive, when you create this response in the ground, you actually create a pulse of magnetic electromagnetic energy, which generates a secondary response in the ground. The currents will not go deep. All currents like to go along the path of least resistance, and that is the highest conductivity. And if that happens to be at the surface, well, then it'll just go along the surface. No one doesn't need to go down into the ground. If the ground is resistive and not very strong, not a good conductor, the electromagnetic fields will actually penetrate deeper until it finds something it can flow in, and you can get to greater depths. So penetration of the system of these signal is not just a function of the system, but it's also a function of the subsurface conductivity, how far down you can see. And in EM world, especially in time domain, because we're creating the response, there's loads and loads of different systems out there with different characteristics, generating different shape pulses, sometimes alternating different pulses, sometimes cutting off really quickly, sometimes not, sometimes very high, strong signals, sometimes weaker. All with different strengths and weaknesses in terms of what they can see and what they can resolve in the subsurface. Both increases or often decreases can tell you again about alteration. Alteration is something we're looking for because alteration can be related to mineralogy and mineral deposits. Um, Variation in clay conductivity is it will definitely you'll see that, and also for water, if you see you can measure saline effects, salinity in water. If you're having problems with your aquifers being close to the sea and you're getting invasion of saline water from the sea into your aquifers, you can measure the saline to freshwater boundary because the saline water is higher conductivity, and you see that in the near surface data, so you can measure that too. Just a little thing, schematic about we talk about time domain and frequency domain. In Sander, we use frequency domain. And I've got a colleague, Greg Hodges. I have to mention him. He's actually like a world leader in electromagnetics, but generally a very knowledgeable geophysicist across the board. And a lot of these slides, actually, I stole from him. I told him I was going to steal them because they're good slides. I particularly like this one because it shows you the difference between time domain and frequency domain with a wine glass. If you like rub around the surface of the ring, it's like you're giving a continual low signal. And that's what we do in frequency domain. It's a very weak signal, which means that it's easy. The problem you have with this system is that you're creating a signal, but you will always see that signal in your detector as well. You have one coil, which is generating an electromagnetic field. You're running a current around that coil, and it creates a magnetic field through the core of the coil that changes because you're changing its amplitude all the time up and down. So that changing magnetic field is sweeping through the earth beneath you, and that's a conductive material. So you do your basic right-hand rule. You've got a changing magnetic field and a conductor. It generates a current. What do currents have related with to them? They have secondary magnetic fields, which will then be detected by the detector. It tells you about the conductivity in the ground. That's your basic EM theory in a nutshell. If you really, the actual mathematics behind it is a bit hairy, but that's how it works. Um, so in one case, we have this, we can measure quite shallow, close to the ground, because we've got this relatively weak signal that we can back off and see the difference that comes from the secondary response, which is what we want to see. That's coming from the ground. And actually, what we see is a phase shift. We see a shift in the signal when it comes back. It's a much weaker amplitude, but it's shifted and it's delayed. And the more resistive the rock is in the near surface, the more delayed the signal is. And so that we can leverage that to figure out the conductivity and resistivity in the near surface. And if you run at a slightly lower frequency, it will penetrate a bit deeper. So we run with four different frequencies, which gives us a bulk resistivity for the nearest few meters, then another 20 or 30 meters, and another, and then eventually down to 120, depending on the conductivity of the material that we're flying over. So we're getting a change in bulk resistivity with depth. So we got a structure in the near surface, which you can which we can figure out. But because it's a weak signal, it doesn't go very farther than that. So it's a really good near surface method. Time domain, on the other hand, it's like you clinking the glass. You want to give a speech at your daughter's wedding. So you go tink, 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 tink. So you're sending out a signal every second or so. It depends on the system, how frequently you do that. And then you listen and you wait, you get the response. So you have the signal, the response is gone. Now you can wait and get the response, the secondary response. So you don't have to back it off. You've turned it off. The problem is that turning off isn't something you can do very quickly. If you turn off the power of something in a big coil or you're running a current through it, it doesn't just disappear immediately. It takes a little while to go. And in that time, that's the near surface response. That's the earliest response is coming from shallow, and the later response is coming from deeper down because the current is flowing deeper into the ground. And so you can't get the near surface from a time domain, but you can get deeper because you've got a much more powerful signal and it will go down into the earth and you can wait and see the response that you get and that's going to give you the conductivity at depth. So these two methods have two different strengths. One is more better for near surface, the other one's better for depth. As I mentioned, though, even for the strongest systems, we're not talking, kilometers into the surface. We're talking usually at best half of 500 meters or so. It's often less than that. But fortunately, most of the mineral deposits that we're interested in are in that range. I mean, you start putting them down much more than that, and it's a bit deep to get. It's a lot of digging anyway. So, might as well get the stuff. Fortunately, a lot of the time, you're not too concerned about what's right at the bottom of the crust. You're not going to get down there anyway. So here's a twin otter. We have two of these guys. And one of the nice things about this plane is that we can put a lot of equipment on it. We can put a gravimeter in there. We can put gamma ray system in there. We can put a stinger out the back and magnetometer. We can't put wingtip magnetometers on this guy because that's where our frequency domain system is. And the transmitters in particular will screw all the mag up there pretty badly because there's lots of magnetic field associated with those. They're generating them after all. So there's no gradient. We can't do mag gradient with this thing, but we can do straight single magnetometer measurements. So we can do it all at once, which is great. I mean, obviously, very cost effective. If you want to do a survey this way, you get lots of bang for your buck with spectrometer packs and EM and gravity all at the same time. And you see we have the four transmitters. These are coils. The system is set up so that you have different geometries of structures in the ground will be more sensitive depending to your signal, depending on the orientation of those coils. Anything which is like coplanar to those coils, so like perpendicular and vertical structure in the direction of flight, if it's perpendicular to us, that's going to couple with the field the most and give the strongest response. Something that's parallel to the direction we're going in vertical will not necessarily, we may not even see it. It may not it may not couple with the magnetic field that we're generating and create a response that we can see. The responses you get for mineralogy, it can be very complicated. It's just, you can get the sense of that from what I'm saying with the geometry being a big factor. But if you're just mapping near surface resistivity based on layering, you're not worried about any of that. You're going to get that for sure. Here's our ranges of conductivities. Here we usually use a resistivity at the top, and conductivity is just it's reciprocal on the bottom there. The same thing as I mentioned. So pyrrhotite, very, very, very conductive clay, graphite, right up there. You see those. Most of the rock types are on the lower side. Um, and yeah, and it's an exponential range, as you can see. Small changes mean a lot in resistivity world. So we have plot it on a exponential scale. So if we're going to find deposits, we need to have high resolution data. We need to consider the geometric sensitivity of the body, which direction we're going to fly, what we expect to see. Is our methodology sensitive to the target? Is it going to be, is it dense? Is it magnetic? What's the host rock? So if it's dense, but it's in the same density host rock, ain't going to help. They're going to be the same. So you have to know what you're looking for, have some information, some sense of what it is, and model in advance, figure out things. Don't just go in blind. Think about what you're going to do. Is it going to work? Do we have reasonable expectation? Of course, you never know for sure. If you did, you wouldn't have to do it. But you can get yourself a better chance of success if you consider what it is you're trying to do. For mapping, we're looking at just bulk rock properties. Um, we don't have to have such strong resolution in the data because we're not looking for little mini bodies, and we want to have stability, consistency over a period of time, and lots of data sets, as many as possible. Is always going to be good to differentiate all the different things you might see and see the boundaries and structures. How do we fly our surveys? Well, typically we fly a grid, normally perpendicular lines. We'll have in this case, the lines going kind of to the north, if you like, are our traverse lines. These are the ones which are closest together. We usually fly those if there's some sort of dominant geological trend. We usually fly perpendicular to that. That's going to give us the most sampling because we're measuring at a very high rate. Ultimately, after we downsample our originals, like we 120 hertz for gravity, 160 hertz for mag, 1 second for spec. For the mag and the gamma ray, the mag ends up at 10 hertz when we deliver it. But still, that's every 7 meters a measurement along every line. So you're getting lots and lots of detail along the line. But of course, if you don't have as much across the lines because the lines are spaced out. There's no much point in flying lines closer together than the height you are above the ground because you just oversample the signal, but there's no extra resolution to be gained. But if you spread data lines out more, then definitely you're going to start to lose detail. So you want to fly reasonably tight line spacing, and that's typically anything from a very tight line spacing would be like 50 meters. That's really, really detailed. 100 meters, 200 meters, pretty typical, 250, 300. Not unusual, especially for regional mapping. 500 now you're starting to get sort of, pretty regional, not very detailed, and then even a kilometer or even 2 kilometers for very large areas. So that's going to set a limitation on your resolution from between lines. Even never, but you're going to get lots and lots of data along the lines regardless because of the measurement rate. So you're going to get the best bang for your buck if you can fly perpendicular to the major geological trends because they're going to be able to interpolate those across between the lines. Of course, we all know that over the geology isn't like that. It doesn't have only one trend in it, but you often do have something that you can work towards. But then you also have to you have these other lines going at perpendicular. We need those in particular for magnetic. Less so for gravity, although we use them for gravity too, and also to some extent gamma ray, and not at all for EM. And they are used to correct for temporal variations in those other techniques. They're called tie lines, and you need those particularly for magnetic data because the Earth's magnetic field is changing all the time. When we fly our surveys, it's not stable. And what we do actually, we monitor the magnetic field at a static point close at one or more locations around the survey area, usually one where we're operating from. And if we can get some into the survey area as well, depending on practical considerations, then we will. So you can monitor magnetic change, which is due to the magnetic field changing in time. And you get sometimes, we'll hear about mag storms. Well, they happen. That's extreme magnetic change, and that can be too high for us to correct for. So we can't fly at those sorts of times. But it's happening at a lower level all the time. There's no time when the magnetic field is not changing. It's always being perturbed, and we have to monitor that and remove it. By monitoring on the ground, yeah, sure, that's pretty good, but it's not exactly perfect because it's only measuring where you are on the ground, not where you are in the airplane, and they're going to be different. It changes over space. So that's going to help you correct for that effect, but you need these tie lines to finish the job off and remove and make the traverse line data consistent line to line to line, so you can make a nice map which is not full of weird streaks related to variations of the magnetic field. The gravity meter doesn't have that problem, but it does have a slow change to it. So it doesn't need as many control lines to correct that. It's relatively easy to correct for. You can get nice profiles from the EM along those lines, but you can't actually level EM using control lines because of the coupling effect I mentioned. Your geometry of detector to geological response is at 90 degrees, and so they're going to be different. So you don't expect to see the same thing where they cross over. So you can't use it, but it's still a useful profile of data in that direction with which will detect things which are oriented differently. So they're still useful, but they're not going to be used to correct the primary data set. It's going to be a lower resolution set of its own if you happen to fly them for that purpose. And they can be helpful for gamma ray data because sometimes you have issues with conditions on the ground changing. It's quite common to fly long surveys. It might rain, the ground becomes wet. That reduces the gamma ray radiation, so you get lows in your data from some lines and relative to other days. And you can use a line that's flown perpendicular to them to help you to figure out what's happened and correct for it. It's not an exact science, but it's very useful, and we've leveraged that in the past for gamma ray as well. And then we basically want to fly low, as low as we safely can. If you get down to 60 meters in a fixed aeroplane, I can tell you, you feel like you're low. The ground seems awfully close. And it is a fact of life in airborne geophysics that it's a dangerous business. I have to say, Santa Geophysics, we've been operating in the airborne space for 60 years and 80 years of total business, and we've had no significant accidents in our entire history. I, there is no other company that can say that, unfortunately. It's because low flying is dangerous. That's a fact of life. You don't have a whole lot of time to respond if you have a problem. So the ground is awfully close. But what we also want to do, we want to fly low as we can, but safely, but we also want to fly relatively consistently, not necessarily at a flat level, because that means we would have to take the highest point in the whole area and fly at that level. And that could be, so you could be way above the ground when you could easily get further down, lower down in other parts. So what we do is we fly a drape surface, and you can think of like if you take any topography and you throw a blanket over it, and it sort of sits on top of the high points, and then you raise that up a little bit so that you crest over the top of the high points by a certain minimum amount. That's your drape surface, and it's all determined by the climb rates of the aircraft that you're doing. Now, obviously, a helicopter has excellent climb rates. It can go vertical, though you really don't want to do that, especially if you're towing a bird. But fixed wing airplanes have their limitations, but they're cheaper. So most of the time you're flying fixed wing because the costs are less. And then you figure out how you can go up and down. You calculate the surface that you can fly in both directions because you want those intersections to be at the same height. You don't want the plane to be flying way higher or way lower when it crosses the other line. You want to be close to it. Within 30 meters or so is usually acceptable. And then we can normally get it less than that, within 10 or 5 if it's not too bumpy up there and flying in good conditions. And you're being guided by GPS the whole time for height and along the lines. So most of our surveys are flown in this drape mode. That's how we do it, up and down those lines. the height above the ground really matters, or height above the signal. This just shows you how either a gravity or magnetic anomaly, depending on how big it is, falls off with height. The smaller the anomaly, which is that yellow line, just like a 200-meter wide anomaly, drops off really fast. So by about 400 meters above the ground, you've it's gone. So attenuation of signal is related to how big the signal is, how wide the anomaly is. Big. So this is why when you fly over the geology, you see signal from the near surface and the magnetics and the gravity, a greater detail than you see from the deeper surface. It's much deeper down. You see less detail. And obviously the same thing as if you fly high above the ground, you have the same reduction in signal. So we want to be low. And that just sort of gives you an example. We had a survey in PNG where we actually had overlapping surveys. One had to be flown really high because it had lots of mountains, and then it actually partially overlapped to an area where we could fly really low over some flat area. So basically, the topography is that green down there. Um, the orange here is line in the top one. That's our flying height. We're having to climb up and up and up to the right because by the time we get to out of that picture, the topography is going really high, and then we had to get up there in order to get to that altitude. Whereas the pink line is where we're flying when we didn't have to go up over the mountain, we turned around. So we stopped and turned around and didn't have to climb up. So the light blue line is the magnetic signal from when we flew high, and the dark blue line is the magnetic signal from when we flew low. And you can see the relationship between the two, but you can see some of the detail is completely gone. The bigger anomalies are still there, it's still going up and down, but they're attenuated in their size. So that really tells you how important survey altitude is if you want to really stay low. And if you're ever interpreting magnetic data, you cannot interpret it unless you know the height above the ground that it was flown, because you'll see changes in the magnetic signal in your map that you might think are geological, but they're not. They're just related to the fact that you changed the altitude was higher in certain areas that related relative to others. So you have to understand both the methodology and the way it was acquired to really be able to interpret it properly. For gamma ray, we mentioned that radiation gets absorbed in the atmosphere. Depending on its strength, it may not get more than 200 meters. Usually we say 300 meters is kind of, we hope to get to 300 most of the time for all of the potassium, uranium, and thorium. The uranium is often the weakest of those and may not always make it to 300, but often it will. Sometimes, and in some cases, we've got up to 450 even with strong signal from the ground. And you're going to do better if you have more of those crystal packs. The more of those packs you can put in, the more gamma rays you're going to capture because they're just shooting off into space in all different directions, and you just want to capture them as you want to grab as many of them as you can. So more detectors means more surface area at the bottom, pointing towards the ground. You'll see more counts, and you'll do better. The downside is I mentioned they're like super heavy, so you pack your airplane full of those crystal packs, and now you can't climb as much. So you've got you can go higher and get better data, but you can't climb up and down as quickly, so you might not do as well. So you have to trade those two things off depending on what the topography is. So those are things which you have to try to deal with. And as you go up, when you're counting your count rate, you're not just measuring from the surface immediately below you. Radiation is coming from all directions, and as long as it's within the range that the radiation can get to you, it can come from the side. So you basically get a footprint of data. Most of the data is coming from within the area beneath you, but gradually, you're still getting data off to the sides, up to, even 500 meters off to either side potentially. No nice picture for EM. I just had to mention it, but yeah, it drops off really quickly with height. So this we really have to optimize flying low, which is why we use our twin otter because it has really good climb rates up and down. Basically, you start to lose signal around 75 meters to 150, usually around 100 meters. You lost it all. So you really have to belly scrape to get good EM data. So here we just mentioned, ranges of data, different systems, rock properties, EM resistivity, quite a broad range, magnetic sensitivity to gravity, not much of a range at all, really. You have to be sensitive to those different things and the different methods. But the more methods you have, the better off you are. Okay, so but geophysics is all about, it's all related to geology. It's really all geoscience. There is no geophysics in geology, really. It's all geoscience. And it's just linked through rock properties, resistivity of the rock, susceptibility, density, and radio element concentrations. It's all the same thing. So yeah, it's just a sort of our whole idea of multiple sensitivities. You've got two things. You could got, overlap. Okay, density could be one or the other. Yeah, another opportunity, you got something now. You got resistivity and density, reducing the possibilities. Three, even less possibilities. You're cutting down on what can be what could be that you're looking at. So the more properties, the better. So here, look, some data. So this is a survey from Quest West. Now the surveys, the stuff I'm going to show you, this stuff is public. You can go to Quest West and Geoscience BC, and you can download this data right into your favorite GIS package. If you use QGIS, it's free and you can become a geophysicist, play with geophysical data, no problem. Nice maps. So this is a gravity survey, and we flew in the British Columbia in the mountains. So lots of topographic effect because often, obviously you have to correct the density is not just rock type, but also is there any rock there at all? If there's a mountain, that's going to cause a gravity high. Well, the mountain's there, so you can correct for that. And this is the 3D density model that this is done by Mira Geoscientists. Geoscience is a consultancy in BC that took our data that we collected for Geoscience BC, and they came up with these. They're looking at anything that's higher density, basically an anomaly. This isn't the actual density, but the extra additional density beyond what's expected in the area. They modeled all of these high gravity bodies but they also did a magnetic susceptibility to property inversion, basically cutting down on the number of what it is, what was likely to be, and these are the different lithologies that would fit into that particular group that they were trying to aim for, and then they come up with a pseudo geology. This, if you actually look at geology map, you can relate some of these different colors directly to mapped geological formations. And you're not seeing the surface, so you're not going to see a one-to-one with a geological map. You're seeing into the subsurface. You will see boundaries, you will see structures that are directly related to mapped lithologies at the surface and boundaries of faults and known faults. You'll also see that sometimes the geological mapping isn't right. This is, geology depends on outcrop. It also depends on the geologist knowing that you go getting it right when he saw the rock, and sometimes it may not be. He may be confused by a piece of rock which isn't actually outcrop. It looks like it is, but it may be transported. He may get it wrong, or there may just not be. He may have to interpolate because you're only seeing rocks outcrops in certain places, and you draw the boundary where you think it is in between the outcrops based on whatever information you have. The geophysics is going to help you to discriminate those boundaries and join the dots. So just to mention here, just in terms of mapping, we've done this. These are large scale mapping surveys which have been carried out. Other than Finland, Cassandra has been involved in all of these, and we'll see some of the Irish data coming up. These are big mapping projects. They're trying to cover almost the entire country where they can. Australia is particularly advanced in this regard. Malawi, we basically through the whole place. So here's Malawi. This is the survey we did for them. There's the country, and there's a few places where we couldn't fly. If you see down the south, we didn't get up to the border because not every country would allow us to fly into their airspace. So Mozambique didn't give us permission to fly in. which means you have to turn around before you get to the boundary. That's why you couldn't go there. Zambia said, yeah, sure, come on in, turn around, go around back. So we could get into Zambia. We could fly right up and beyond, up to the border and then turn around in Zambia. Same with Tanzania. We did a little bit of gravity over some targeted structures that the client was particularly interested in. The Geological Survey of Malawi was the client. They had some deep basin structures they were interested in. You can see those low gravities due to sedimentary basins. And then there's on the right there, there's gamma ray data. So we did mag, some gravity, and gamma ray. And mag and spec, as we call it, mag and spectrometry, gamma ray spectrometry, those are common combinations. And particularly now, these are the two things that everybody's flying because they're all looking for critical minerals. And these are the two best methods to do that. So the United States is looking for it, Australia, Saudi Arabia, Canada, the Europeans, you name it, everybody's got after it because they understand that it's not just a matter of being out of them finding them, but having control of them as well, because they're considered technologically important, and also you don't want to be beholden to China, for example, for your supply of these minerals for geopolitical reasons. Yeah, so everyone wants their own mag spec. That's what we're flying, loads and loads. We used to fly tons and tons of gravity because it used to be like for a number of long years, it was oil was the main target, and deep basin sedimentary structures was what oil companies are interested in, and air grav is absolutely perfect for that. So mag and grav, lots of those surveys. Now we fly hardly any of those. Do still occasionally. There are companies out there still looking for new oil fields or to better characterize the structures that they already know, but way less. Now it's all critical minerals. Here we have magnetic gradient. This is actually just it's a gradiometer survey, so we've got magnetic gradient there. We've got gravity gradient, which is we didn't measure it, we just derived it. You can calculate these things from the data you've got. You can either measure gradient or you can calculate it based on potential field theory. And on the right, you've got this nice gamma ray ternary. This is where you combine uranium, thorium, and potassium together into one image. The pinker it is, the more potassium, the more bluey it is, the more uranium, the more yellow, thorium, and everything in between colors of combinations. And the higher, stronger the color is, the more intense the signal was. You can see some gaps in there, some white gaps. That's where we flew too high, or there was a lake. So in some places, there's Lake Malawi there on the right. You don't get anything there. But there are also bodies of water and reservoirs and the like. But there's also high mountains, which we had to crest over. And of course, you might get something at the crest of the mountain and you get something on the approach, but you don't get anything as you're climbing up to get over the mountain because you get too high. And some places we actually flew special lines just perpendicular to the mountains just to get in lower, to get gamma ray data in those areas where we could. But that's a really nice surface kind of response to the near surface regolith and its relationship to the underlying geology. So we look at some detail there. We look at the magnetic gradient and that area there. So here we have potassium on the left, just straight potassium, and we have what we call the first vertical derivative for the magnetic anomaly, calculated from potential field theory. How fast is the magnetic field changing in the vertical direction? You can do that with just math. And you can see there's some things which are in common between these two. Can you see my cursor? I don't know. Can you see a little blob here? So there's a nice magnetic body there. That's some sort of intrusion. And it has a very strong potassium concentration associated with it. So that clearly is some kind of granitic body that's related, that's there, that's intruded in there. You go there, and you're going to find something sticking through the ground, I'm pretty sure. Then you can see here some nice structures, folded layering in the magnetics. You can see some extent in the gamma ray. So some of these layers are potassic, but other ones are not. So you can see that all these structures here in the magnetics, you see boundaries, you see faults, you see folds, lots and lots of structure. You can see some of those things also in the gamma ray, but you're also seeing changes in the surface, the nature of the lithologies, but also overburden. So this whole area here, which is lower, may be more likely. You can see there's no big change in the mag, so probably, and this is high frequency mag, so it's probably close to the surface. This is probably some sort of sedimentary cover, shallow overburden over the top, obscuring the geological features here. But where they're related to ridge, often these will be physical ridges as well and hills. The bones of the ground stick through. You get the gamma ray related to the actual rocks, and you get some actual signal related directly to the structures that you can see. Here's something a little closer to home for you guys up in Northern Ireland. We've done a survey for the Geological Survey of Ireland. It started for the British Geological Survey actually before it was flown by a different actually by the British Geological Survey itself. They flew Northern Ireland. Then we bought the plane off them, and then we flew the rest for the Republic of Ireland and to some extent the British government when we did a survey around the edge of Northern Ireland. We're now in the process of trying to finish off the last bit of Ireland. We've flown pretty much the whole country. These images are from earlier in the program. We do a chunk every year, and we're now doing our best to try to cover the last part, which is the hardest part, the mountains in the southwest of Ireland, which are brutal to fly in, absolutely brutal. The weather is terrible. It's Ireland, right? It rains. Visibility is awful. To rugged topography, so hard to fly in. Yeah, it's tough, but we got the rest done. So again, this data is public data. You go to the Geological Survey of Ireland's site, search for their TELUS program, TELLUS, download data. You can get gamma ray, mag, and EM, frequency domain EM data. So here we're just looking at the effect of the if I can of the you can quite clearly see where those lavas are, the Antrim lavas stick out fantastically in that magnetic intensity field. Like, that's really, really obvious in the boundary of where they occur. And of course, they're very well mapped because they're very clear, they're easy to map. But there's even variations within there. And there are other things going on. There are dikes running through which you can see having a magnetic response that comes in from you're seeing it through beneath the dikes, beneath the lavas, and they come out into the area where the lavas have been either that didn't occur or have been eroded. Here's the gamma ray ternary, slightly different version of the ternary. It goes kind of a nasty dark color where it's where it's high. I prefer the bright colors myself, but still, you can see the difference. You can see the signal directly related to that, very close at the surface. So yeah, I mean, we all know there's soil and dirt, covering those. It's not like you walk to around Northern Ireland, you're walking on lava fields, but quite clearly the underlying geology is reflected in the gamma ray, even though it's coming from that top few centimeters of the surface. So you can't, you shouldn't consider just because of that it isn't telling you about subsurface geology. But you do need to consider it because you're going to see rivers, you're going to see transported signal, all those sorts of things. Here's the resistivity. Not quite as obvious correlation, but definitely something going on, much higher resistivity. But there are other high resistivity areas here which are due to other formations. So, again, it's a matter of discrimination. Different methods, different techniques are going to show you different things. So this is a study. This is actually a study in an area in Canada, which we did for actually for a potential nuclear waste deposit repository. This is somewhere where Canada is like many countries trying to figure out where to stick its waste. And this is one of the possible places we did a gravity project here to help. We also measured magnetic field at the same time because it was easy to do. Over the Revel batholith. This is one of the places that's been considered as a potential location to dig a hole and bury some of the nuclear waste. So you can see here, this is the gravity. The Revel batholith has generally a lower density relative to the metasedimentary bound layer, which is wrapped around the outside of this structure. And this area is covered in swamp and trees, and it's horrible territory to work in if you're going to do it. You'd never be able to do this sort of work on the ground. It would just be, you can follow up in detail, but to try and do a large area like this would be very difficult. Here's the geological map as it was before. You see this Gravel batholith, this granodiorite, these metavolcanics, mostly mafic and intermediate, with some metasediments and some dikes. Geological mapping. So people have been there with their hammer and their bug spray, if you know Canada, and they've mapped this thing. Okay, so here's the vertical gradient of that gravity, and we're starting to see more detail in the structure. There's things going on. So, you can refine this and we can model this, and we actually model the depth of the granite from the gravity data. So not only can we see its spatial extent, but we want to know how deep it was. We couldn't actually say for sure where the bottom was because there's always some ambiguity in modeling. Unless you drill a hole, then you will know, and but that's an expensive business. But we could tell that it was at least 3 kilometers deep. I think I remember, if I remember rightly, or whatever it was. Enough was the point. Deep enough was the key thing. More deep enough that it would work for what they wanted to do, because they're not going to go deeper than that, and they also want it to be, solidly encased within this coherent and batholith of granitic material. So here we can see, you can basically some of the interpretation of that. Got the high areas and the low areas, and you can start to refine maybe some of those boundaries where the metavolcanics really end and where the batholith really starts. And yeah, the mapping is good, but it's not perfect, and that's what you'd expect. So you can refine the mapping. You look at the mag, and then all of a sudden something different turns up. These dikes show up lovely. Yeah, okay. That dike stopped there. Well, obviously it didn't. It keeps going here, right? You can tell that. So, there's other dikes and things going on, but there's also, oh, what's this? There's something turned up here that wasn't in the gravity. So there's something different in that part of the batholith that wasn't picked up. And there are other things. And then there's this nice structure here. What's that? That's kind of semi-mapped, but so it's not in the gravity, so it can't be it looks like something a very high frequency, so it's obviously near the surface. It's not showing in the gravity, so it's probably not very thick. It's not really affecting the gravity signal. So it's something, just a layer of magnetic material, probably the same material that's on either side, but here flat lying, so you don't see the layering in it so much. So it's basically probably what was wrapped over the top of this granite when it was intruded and pushed up into these metasediments, or it could be something different. But either way, it's you don't expect to see granite if you go there, or you're going to see something different from what from the main granitic batholith. So you probably don't want to drill your hole there because that's probably going to be something difficult to get through. So as you see, no gravity, so something flat lying and magnetic. And then what about this? This was mapped as ultramafics, this band in here inside the sediments that are wrapped around the outside. But, it's not high, it's not dense, and it's not magnetic. So it probably isn't ultramafics at all. So that's a case where the boundary is there, but they got it wrong. I mean, the properties are completely wrong. So go back, check it out again, and figure it out again. So some things are like, okay, yeah, this is probably not what you got. So mostly geophysics is like, you're going to use it in combination with the geology. Neither's right or wrong, but it's all data. Data has to be all sources of data have to be reconciled and have to come to a common model. Something and also something which we believe is geologically feasible, which is based off of, all of the experience and knowledge we now have of how the Earth works. Is it likely to be, what we think it is in this particular location, as well as what does it fit all of the data, and come up with a geological model, which you will then find some more data and change, because that's what you do when you get more data. You get a better model. So you can't be wedded to one idea or another just because you think you've seen something. All data has to be reconciled and has to be explained in some way or other to come up with something that explains everything you see. So, as I said, low density, low mag is not ultramafic, is something else. And we've got some other thing here. So we're refining the geology, as well as modeling the granitic batholith at depth. So this is always working together to give you a better view of what's actually happening. Yeah, so it's all about detectability in the end, measuring multiple rocks of properties. You want you need instruments that can detect the range of the types of, sensitive to the changes that you need to be able to see, to tell the differences that you're looking for. And relatively speaking, airborne survey is a way of covering large areas relatively cheaply. It's something at the start front end of most exploration programs. Seismic data is expensive to collect, really expensive. Drilling is really expensive. Ground gravity and other methods and ground mag and all that is fine, but slow and hard to do. So you can get a lot from this. There's a lot of bang for your buck from an airborne survey, and you can then follow up with your more expensive methods and the like, and have in the areas of greater um, prospectivity or of interest, and you can go in on the ground and do detailed work where it seems to be worth it. So it's quite frequently something to do early in your exploration cycle. And I think that's it. I've done talking. Blimey. How long was that? I don't know.
Thank you very much, Martin. Would you like to stop sharing so that
Yes. There we
lovely.
go.
Well, I found that fascinating. I didn't realize how, we use these techniques and you could actually do them in one flight over, so to speak. And when you were talking about looking for a nuclear waste deposit, it's particularly important to find the right place, isn't it?
Well,
Yeah,
for sure.
you know,
Well, yeah. I mean, it's very controversial. The whole thing, just anyone puts a nucleus this stamp on the side of anything, and it's like people freak out pretty much. And I mean, I'm not in part of the decision-making process, but I've spoken to those that have been part of that, and yeah, it's a very long, drawn-out business. But I think what we did, if it ever comes to pass there, I don't know whether it will, but I think what we did there was good work. Yeah.
well, definitely. I mean, the thing is, it's a lot cheaper to do one of the surveys you've got than to make a mistake and start building a facility in the wrong place.
Absolutely, yeah. Yeah, I mean they obviously will drill there to tell,
Oh, yes.
to make sure, but they have to have a reasonable expectation. If we told them, well, this thing's probably only like, 500 meters thick, and then they're gonna, okay, they'll go somewhere else.
Yeah, I mean,
They
it's
won't
not
even
worth
they
it,
won't
is
even
it?
do it. That's right. Yeah,
You know,
you
you go,
de-risk.
you go look,
De-risking is what it's about.
you go look at the hydrology and everything else as well, haven't you? And groundwater and
Oh
all that
yes.
sort of thing.
Yeah, yeah, absolutely. Did a whole survey around Yucca Mountain, and this is the equivalent depository in the United States. I've had a bit of a record there, um, flying for the USGS for exactly that, all to do with looking for fault lines and fractures basically, will Yucca Mountain leak was
Indeed.
was the whole thing. Yeah, so and that's so we did a big mag survey for that all around that area to help them to understand the risk of that. But even that, which has been fairly in the, I don't think they've even started using that. Yeah, I don't know what, but again, it takes a long time to
Yeah, big
persuade
things.
anybody to put nuclear waste anywhere
Well,
other
you've
than
got to
where it
build the thing,
happens to
haven't you?
be.
Yeah.
Yeah, yeah, that's right. So it just sits around
Mhm.
waiting for someone to do something with it. It's
Right.
usually, but yeah.
So, does anyone have any questions for Martin?
Martin, can you hear me?
Yes.
Yes.
Okay. I seem to remember you talking about on the magnetic surveys, you could see vertical structures, something to do with diamonds. Is that right or not?
Well, vertical is more apparent. Horizontal structures are not as apparent. You've
Mm,
got layers, but you've got the boundaries of horizontal things. So, like an edge of a sill or a fault line between two bodies of different magnetic properties that are offset, or the fault line might just have show up because it's you know um, demagnetized or actually magnetized. It can be high
mm,
because it's got magnetic material that's been deposited in it, or it can more often just eroded and broken down and low. So vertical structures tend to show, but boundaries of horizontals, edges of things, you'll see those, but flat lying things, not so much. So, that's why it's a lot of people are doing sedimentary sequencing and for oil structures like will combine the mag with the seismic because the seismic's the opposite. The seismic's great for horizontal structures, but
mm.
not so good for vertical. So they make a really good combination when it comes to structural mapping and basin analysis.
Wonderful. I mean, the thing is as well, if this data is made available more freely, it presumably feeds into geological research as well.
Yeah, well, I mean, the thing is, some of these countries hold their data very close, and other ones put them say, "Here it is, go at it," and they'll throw it out on the internet, and you can download not just maps but the raw data.
Mm.
Obviously, often they're trying to spur um, companies into exploration programs, so they're doing the upfront part for them and say, "Okay, here's this data, look, all this area, go look at that." See if you can see something that you find interesting and go and look. And so, that's what India is doing, that's what the US is doing. This data all becomes publicly available at some point, but it also can be used by the academic community as well. Um, and it's free to use and yeah, it's packed with stuff. It's packed with potential, if I can use that bit of a pun, but yeah, the information, there's so much. Yeah, we do some interpretation of this work. Sometimes that's part of the remit that we have, but often it's not. It's just we will just hand it over. Here's my baby, go with it, and they'll take it and they'll do, and people will have at it, and that's fine. That's the good. You want to maximize the use of this sort of information, and that's what you hope will happen when you do these surveys, especially in some of the further flung parts of
Mhm.
the world where you're looking for to stimulate activity, and often they're funded internationally. Like that Malawi survey. I think that was a World Bank funded project. So they're trying to stimulate activities in third world countries like that.
Then Kathleen is asking, does the air gravity method measure density?
Yes, effectively it does. Yeah, I mean it measures accelerations due to density changes, but it's as I said, it's such a tiny effect relative to the
Mm.
all the other things going on. But with the high level, high grade GPS that we calculate, we can remove the aircraft's accelerations from that and recover those density changes. So yeah, and we're getting subsurface structures as a result, or lithological changes.
Malcolm, you have a question. Please go ahead.
Yeah, I think you slightly touched on this, but just given the current geopolitical situation, are you seeing an increase in business, requirement of the information that you produce?
Yeah, primarily it's governments because they want to, and as I mentioned, it's the geopolitics of this. Like if you look at everyone knows about rare earth elements. Okay, you've heard of those. They're in your cell phone. They're in the every electronic, EV cars and all that, in high demand. I always say the funny thing about rare earth elements is they're not rare. They're actually all over the place. But the problem is that they're not concentrated like all other. A mineable deposit means you have to have it concentrated. And till now, the two most prolific places from rare earths are China and the Congo. DRC, well, southern DRC, it's unstable, let's say. And then, of course, there's China, and of course, the concerns Western countries in particular have is over control of the supply. So yes, there's a lot of different countries that would rather have their own rather than get them from somewhere else. They want to have control of that supply, and preferably within their boundaries of their own country. Although, of course, Canada, we have this whole Trump thing going on, and that's the 51st state thing, and Greenland and all that. That's all related to the fact that they're there. These deposits exist in Canada and in Greenland, but whether they're mineable, that's another matter. But the potential is actually quite high for those sorts of things in those areas. You just have to look more closely. Of course, Greenland is covered with ice, but gradually becoming less covered with ice. So, for better or for worse, their deposits are appearing, and they have to handle the geopolitics. They're in a bit of a tough spot because they've got to figure out what they're going to do about that.
Yeah, indeed.
But certainly Canada should be looking for more of these things, and definitely other countries are that we're working. That's what they're all looking for. Yeah, so that's really driving our business a lot right now.
And is there a specific part of the world where you're seeing more business coming from? I mean, obviously China has reserves, well-known reserves, but are you seeing other areas of the world really trying to step up and step in, particularly, or is it coming from everywhere?
Well, there are countries with ambitions, I would say. Like I mentioned, I'm going to India and to Saudi Arabia. Those are countries that project a certain regional power, if you like, and the US, of course, we know. So those are the places that are doing it for the most part. Countries that are kind of like a little bit not so concerned about the world pecking order, not so much. So
Well, I'm sorry to say that we're probably going to have to draw to a close now in case this particular Zoom channel is needed by anybody else. So I think if you could all come off mute, please, we'd like to give you, Martin, a good round of applause for a very interesting talk. And thank you for letting us record it as well for all those who couldn't be here this afternoon. So thank you for your time. And if you do have any more conferences to go to, I hope they are enjoyable today.
Sure.
Thank you very much, Martin. Thank you.
Thank you. Very welcome.
Thank you.
Enjoyed it.
Yeah, take care now. And I'll see the rest of you in January, because the next meeting would be just before Christmas, and that's probably a bit too pressured for most people. So I'll see you in January, and have a great Christmas and New Year until then, all of you. Thank you very much. Thank you.
Cheers.
Bye.
Bye, Ian.
Safe flying, Martin.
Cheers.
Right, thank you.